they're now here, right? So we can separate what's endocytic, what's plasma membrane. Basically, you can now follow endocytosis in the context of the animal. And you can ask a lot of questions. In particular case, we're comparing the dynamics of brain and muscle. And if you're interested, we can go into those details. I mean, it's not so important right now, just to indicate that we can do the analysis of things. Okay, I've been interested for a long time in what happens when a cell, when it divides. Some years ago, we found that when a cell divides and goes through mitosis, the volume is roughly constant, but the cell loses surface area in mitosis, and then the two daughter cells massively recover surface area when they do cytokinesis. So this particular movie, where now you see the single isolated cells, we're tracking the plasma membrane, we're also tracking organelles. So I can also tell you where the location of the organelles are as the cells are dividing. So we have hundreds of cells that we're tracking here, and this happens to be now the brain, which is a rich tissue where you're getting a lot of what's called asymmetric division going on. So the cells are taking decisions to decide whether you're making a neuron or other cell types. So again, the trick of separating the cells from each other.
How does that work? Is it manually traced out or?
Nothing manual, my friend. No. It's all automatic. Yeah. Yeah. So we're dealing with this, and it's all automatic, right?
So you can go to Paris and have fun.
So this will show you for one cell, just for one cell, what happens on time. So here you're going to have the volume and the surface area for this cell, and what is being plotted here is the relative position of the organelles as you divide, right? So there's some jiggering around, and then there's a reset of the position as you go through mitosis. So for example, the mitochondria go to the periphery of the cells when you divide in metaphase, right? Not surprising, you have all this cytoskeleton that's reorganized, right? You have the microtubules, it's still pushed away. The ER is the same, right? And then you can see here, for example, that you have the surface area of the cell, the interface, there's a dip. So the dip is because, and we found that endocytosis is kept, but recycling shuts down, right? So you keep consuming your membrane through the classroom pathway, you remove membrane as you round up, and as soon as you do cytokinesis, you reactivate the exocytic pathway, and all the membrane comes back, and the surface area of the two daughter cells added is the same as the mother or the father, right? And that recycling depends on calcium and uses the same snares as regulated secretion. And for some of you that have done tissue culture and you see bleeding cells, sometimes one thinks that apoptotic cells, actually the cells that are dividing are bleeding all the time, and that's this particular phenomenon. Okay, I'm going to show you technically how we collect these large volumes. So what you have here is now just a slab. This is a 3-micron slab, and this is a tile of 7 by 7 by 3 of those stacks. So I'm going to show you different regions, how it shows with no correction. Sorry for the light, I don't think you can see that very well, but this is with no correction. This is when we do the adaptive optics, and then finally the complete image. And then what we do is we first do the adaptive optics in the whole volume, and then as we keep cycling stochastically, we go through different locations and we correct. So the correction takes like a fraction of a second, so we don't lose time in the actual data acquisition. Okay, so I'm almost done. This is one more example here. In this case, what you're going to see now is these blocks. So each one of those was one of those stacks. We had to write code to stitch them back together so that the images are all nice. And what you're going to see now is the eye of the fish. And in a minute, you will see that you can see all the texture of the eye. And the reason we were doing this is because the eye is very active in cell division. And there's interesting decisions, again, that are happening in what's called the neuroepithelium that links where the retina is going to appear from the rest of the tissue. So here, Gokul is showing you different ways of presenting the data that's a little bit easier. You can see now where the eye will from. This is one day after fertilization. And then this actually is a movie. And the reason we were doing that is because we were interested to follow what was going on in cell division here. Okay, this is a more canonical way in which you can present. This is an orthoprojection, just to show you the quality of the data. I mean, there's no bleaching and there's no loss of intensity of the data.
How long does this take?
This particular one takes, well, each stack must be, each stack is maybe 3 seconds, and there were 120 of those. Yeah.
So how do you do mitosis? How do you do mitosis? When you look at the mitosis?
Yeah, because the cycle that we're doing is every minute or something, right?
Okay.
Yeah.
So you can just go for hours?
Yeah. Okay, some of you like cancer, so here we go, cancer. So this is an experiment that comes from Martin and Matos' group. So they generated, they provided a human cancer cell that's in green, and then the fish, the blood vessels of the fish are purple, right? And so just to show you the exquisite level of detail you can see right now. You can see the cells, you can see different forms of migration, you have tails and things protruding. And I mean, you can measure the volumes and speeds, and you can do tons of things, right? And so we have done some of that analysis as well. Okay, so I'm going to end with one more fish, one more movie, one more fish. Okay, I'm going to show you in this particular movie. It's very interesting because it's the head of the animal. This is with Sean Megason, a colleague upstairs on his group. So they are very interested in the development of the ear. The fish have ear. I didn't know that they have ears, but they don't listen. They use ear, the inner ear, just for 3D orientation. So we were focused in this region here just to see the early stages of how the ear formed. So just to orient yourself, what is shown here is membrane in color. All the membranes are labeled. This is a transgene animal for cat usage going into the membrane. This is the outside of the animal. This is the skin. There's going to be a capillary here. This is brain. And the point of this movie, as you will see in a minute, is that you will see now the neutrophil, part of the inflammation recognition system. They're going to be crawling here. And I just want you to appreciate the level of detail that we have. And in blue, what you're going to see is dextrin rejected fluorescent dextrin into the heart of the animal. So they also give endocytosis. So you see the blue spot. This is the endocytosis that went on in the endothelial cells. And there you have this guy swimming here. Lots of exploring and going. This is a 3D movie. Unfortunately, I don't have it. I can have glasses. I don't have VR right now to show it to you. This is a 30 gigabyte movie. Fine, it's a bit large. But the level of detail is exquisite. You really can see dark surface structure. Can you just say about the imaging? So the trick is that the astronomers use a laser that shoots out to the light in the sky to create an artificial star. It's called a guide star. Okay, we do the same trick with an X-ray laser. I didn't tell you we use a 2-photon microscope.